secondary and tertiary shade mismatch is one of the most overlooked but critical defects in automotive coatings. While primary shade approval may pass at first glance, panels often fail OEM visual inspection when viewed under multiple angles or light sources. These mismatches are especially problematic in metallic and pearlescent systems, where color perception is highly sensitive to pigment orientation, interference effects, and film build. From an RD&I standpoint, understanding shade mismatch requires integrating knowledge of coating optics, flake orientation, substrate influence, and multi-angle measurement, not just relying on conventional color instruments or visual checks. Visually, secondary shade mismatch appears as a subtle deviation in hue, lightness, or saturation in localized zones of a panel. Tertiary shade mismatch refers to even finer variations, often detectable only under directional lighting or when panels are rotated. For example, a panel may match the target color when viewed frontally but reveal greenish or bluish undertones at 45 degrees or 60 degrees viewing angles. These shifts are amplified in pearlescent and metallic base coats because they depend on flake alignment, interference pigments, and multi-layer light interaction to create the intended effect. The challenge for OEM plants is that such mismatches may pass average color measurements, but still be visually unacceptable to customers. The root causes of secondary and tertiary shade mismatch are multifactorial. Flake orientation during spraying is primary. Metallic and pearlescent pigments reflect light directionally, so any tilting, clustering, or uneven distribution produces localized color shifts. Film thickness DFT variations exacerbate the problem, as interference pigments rely on precise optical path lengths to achieve the target shade. Too thick a film shifts perceived hue, while too thin a film may expose underlying layers or reduce intensity. OEM plants maintain strict DFT tolerances for each panel section, especially for edges, curves, and horizontal surfaces. Additives and formulation choices influence shade uniformity. Flow and leveling agents improve pigment alignment, allowing flakes to orient parallel to the substrate, reducing secondary shade variation. Anti-settling agents prevent flake aggregation during mixing or application, ensuring uniform deposition. However, overdosing additives can stiffen the film or create localized flow issues, causing micro-level misalignment and promoting tertiary shade mismatch. Solvent blends are equally critical. A proper balance of fast and slow evaporating solvents ensures the film remains open long enough for pigments to settle without causing skinning, which would trap flakes in irregular orientations. Flash-off, oven ramp, and environmental conditions directly impact pigment behavior. In high-temperature or low-humidity environments, fast solvent evaporation can induce early skin formation, locking pigments prematurely and increasing the risk of color shift across viewing angles. Conversely, high humidity slows solvent evaporation, allowing pigments to align but potentially increasing sag or microflow anomalies. OEM plants closely monitor booth temperature, airflow, and relative humidity, adjusting solvent blends and flash-off duration to maintain consistent optical properties across the panel. Multi-angle measurement is essential for detecting and quantifying secondary and tertiary shade mismatch. Instruments such as goniophotometers or multi-angle spectrophotometers measure color at multiple viewing geometries, capturing directional color changes caused by metallic or pearlescent flakes. These readings are compared with reference standards to ensure compliance with OEM tolerance specifications. Visual inspection under multiple standardized light sources, D65 daylight, incandescent, and fluorescent, is also critical, as human perception remains the ultimate determinant of acceptability in OEM approval labs. Troubleshooting secondary and tertiary shade mismatch requires a systematic approach. First, identify affected zones using multi-angle measurements and visual inspection. Second, correlate these areas with DFT mapping to detect thickness variations. Third, review spray technique, gun parameters, and traversal speed to ensure uniform pigment laydown. Fourth, evaluate solvent blend, flash-off, and additive levels to verify that pigments had sufficient mobility to self-level during application. Finally, confirm environmental control during spraying, as even minor temperature or humidity fluctuations can significantly impact pigment orientation and visual perception. In multi-layer systems, base coat and clear coat interactions further influence shade perception. Clear coat thickness, flow, and refractive index affect how underlying pigments reflect light. Uneven clear coat flow or localized microtopography can distort reflected color, exacerbating secondary or tertiary shade mismatch. OEM engineers integrate these variables into process windows and visual approval criteria to ensure consistent results across all panels and production shifts. The key takeaway is that secondary and tertiary shade mismatch is not a random visual anomaly, but a predictable consequence of pigment orientation, film build, solvent behavior, additives, and environmental control. Corrective action after panels are baked is limited. Prevention through rigorous process control, DFT management, optimized additive use, and multi-angle verification is essential. OEM plants that master these variables achieve consistent color quality, minimize rework, and satisfy the most stringent visual standards. If you've experienced subtle color shifts, inconsistent metallic reflection, or panels that fail multi-angle visual inspection, leave your questions in the comments. Future episodes will cover clouding, multi-layer flop control, and advanced optical defect troubleshooting, completing the Masterclass on appearance defects in solvent-borne automotive coatings.